How's it going, everyone? This is Conrad from Sloppy Joe Pirates, and today we're going to be talking about Pwn Rickroll. This was a medium challenge. It had 90 solves during the LACTF. In this challenge, we're going to be using printf vulnerabilities 3 times to first change a program execution from single shot to multi-shot. Then we're going to leak a libc address, and then we're going to overwrite a global offset table entry with a one gadget. So all in all, pretty fun challenge. It was made by Applet, so we know it was going to be a good challenge. It says, make your own custom rickroll with my new rickroll program. We're given a netcat port and 3 download files. The first download file is a Docker file. So it's a redpwn jail. If you're new to these redpwn jails, what it's going to do is it's going to download all the libraries and pretty much everything from this Docker image into this folder. And when the redpwn jail actually executes, it's going to do a chroot on this directory. So that means that if you're looking for the flag file, it's not located here on the Docker container. It's actually located here because it's going to do a little chroot. It also means it's going to grab libc and everything from this directory. So if you need libc, you can do a Docker interactive volume mount. So we're going to mount the current working directory, print working directory, to challenge within the container. And then we'll do a tag, this one. Oh, I forgot run. Then, if we want to see which libc is being used, we can do ldd rickroll. We see it's this libc is the one that's going to be used. Then we can do an lsla. We'll see that it's a symlink, and so this is the real libc. And then when we do that volume mounting, it's a two-way mounting. So anything we put in this folder will be accessible back on the host computer, so my Mac. So we can do a copy lib x86 libc and copy it here. So now we have libc if we need it. The real way I recommend solving these challenges, though, is not actually, I mean, you should copy libc if you need it, but is to actually just create a new Docker container that you can play with. And so that way your local system will match the remote system. So in a new Docker file, just do something like this from Debian with this specific hash identifier. And then you can just do update, install everything you need. So apt update, app install. Yes, you probably need GDB, checksec, pwn debug. I think you have to install pwn debug manually, but you know, all the tools you think you'll need. And then from there, just run everything in that Docker file so you know that it's like closer aligned to what remote will be. And this is how I solve all my challenges. So for example, I already have, at the start of the CTF, I saw this Debian hash, and so I made a little Debian container. I just call it Debian Pwner, and I run all my challenges in here. And so when I need to run, Python 3 solve, I know that it's going to be pretty close to what the remote systems look like. So great tip. It makes exploiting, especially like things like printfs, where the stack needs to be aligned the same way as locally and remote, just makes those challenges a lot easier to solve, and you don't get into those weird cases where your exploit works locally but doesn't work remotely. This is the C file. So pretty short program, and I'm very thankful we have a C file. So it says, if main has been called, put nice try, return 1. Otherwise, main called is equal to 1. We're going to do some buffering, print. We're going to do an fgets. The buffer size is 256, and we're reading in 256 bytes, so we're not going to be doing a buffer overflow here. But that's going to do a printf, and a printf. Cool. Like I said, so our end goal is to get shell on the box. And with all of these challenges, we seem to be just using one gadget a lot. So somehow we need to execute or be able to jump to an arbitrary address. To do that, we also need a libc leak. We can see what protections are enabled. So we'll do checksec file is equal to rickroll. And we have these protections. So we can, for our jumping mechanism, we could overwrite the global offset table and overwrite one of those entries with our one gadget. So we have a potential sink here. There's no stack canary, and NX is enabled, but these don't really matter because we're not going to be doing a buffer overflow. There's no pi, so that means that these will be, this function is at a known address, so we could jump back to the start of main if we need to, because we know what its address is. I was thinking more about the challenge. I don't actually think pi needed to be disabled for this challenge, but I could be wrong about that. And what else? Actually, never mind. We do need pi disabled. If it was a buffer overflow, you could do the last byte overflow, but we're not doing a buffer overflow. We're doing a printf. So yeah, actually, it is good that pi is disabled. But anyways, so we're going to do a couple different things. The first thing we're going to do is we need this program to execute multiple times because we need to exploit multiple printf vulnerabilities. So we're going to use printf to eventually overwrite some entry in the global offset table such that it points to a 1 gadget. So that'll be our very last printf. We also need a printf that'll leak libc. And so this is already 2 different printfs, and that's all we really need. But like I said, it's already 2 and we're only given 1. So for our first printf, we're going to have to figure out some way that we can get this program to repeat multiple times. They do some check here to see if main is being called again. This really isn't a stopper because if you can jump somewhere arbitrarily, we can just jump right here in the code, and so that it's not going to do this main check and print out. So I was stuck here for a little bit of trying to figure out how to get this to repeat. Like, we can overwrite an entry in the global offset table, but we still want to be able to use this printf exploit. But if we overwrite the printf exploit, it's the only thing that's being called at the very end, and so it's our only like looping mechanism. So it didn't really seem possible. Eventually, I poked at it in Ghidra just to see if I was missing something, and it turns out I was missing something. So when this program was compiled using GCC, you can tell it's GCC if you do a strings on the binary, but when it was compiled using GCC, it changed that last printf to a puts. So this was our secret. So we can see it goes printf, printf, puts, but here it was printf, printf, printf. So very sneaky. I guess the C compiler just does this sometimes. It is what it is. So we can overwrite the entry for puts such that when puts is called, it'll jump to, let's say, here. And so that way we can loop multiple times and we can call printf multiple times. So that'll be our first part of the exploit. And like I said, once we can call printf multiple times, we can leak libc and then overwrite another. We can just overwrite this puts again such that it calls out to the 1 gadget. Cool. And so that's what the solve script looks like. Here we're just doing the standard pwn tools sort of solve script. We're going to import some stuff. I disabled the bytes warning. I shouldn't do it, but I do. Then we're going to load in the binary, libc. Since we're running on that Docker file that's going to use the correct libc, we don't actually have to load libc. We can just use the local one, which is very useful. We're going to set some context. This does our packing and stuff correctly, 32 and 64-bit, and sets the assembly language and everything correctly for us. Log level debug so we can see what's going on. Terminal, if you run everything in a Docker container, it's easy to use tmux with this, and so that it splits and you can see GDB. Cool, so the first part of the exploit, like I said, is we need to get it such that the program will repeatedly call printf. And so to do that, I'm overwriting the global offset table, and specifically the puts address within the global offset table. And I want it such that whenever puts is called, instead of calling puts, it's just going to jump into some address within main. And so to get these 2 addresses, I do gdb rickroll. Let's a little slow. We're going to break at main. We're going to run. It's going to go here, and we can look at the entries within the global offset table. And so here's puts. So I'm just going to copy this address out. It's something something 18, so it's right here. And then for the main address, I grabbed this from Ghidra. I'm guessing I'm using this one, 117D. Oh, no, I'm using 1187. 1187, so I'm going to here. I'll scoot this over. And so I'm just going to jump to this address. So whenever puts is called down here, or I guess right here, whenever puts is called here, instead of calling puts, it's just going to jump back to here. It's super useful, so we can just call printf and use printf vulnerabilities many times. For actually doing the printf, again, printf under the hood, these we're going to be using that %n character to say, like, you know, printf, when it encounters a %n character, will read the next value off the stack and assign that value. The pointer, it's an int n on the stack. Sorry, an int star on the stack. It'll write the number of bytes that have been written to that value. If you've never seen a printf vulnerability, I'd highly recommend, there's a lot of good videos on YouTube that like actually do the animations and show the theory. This is just what it looks like in practice. So we define a writes buffer, and so we say at this address, I want you to put this value. So at the puts global offset table address, I want you to put the main return address value. And to do that, we're using pwn tools. Pwn tools is amazing. They have this thing. Constructing printfs by hand is super annoying, but it's going to do format string payload. You have to pass it this offset. To calculate this offset, you send this. AAA, %x, 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 and you need to count which one of these %x's when it prints has the AAA. In this case, it's 1, 2, 3, 4, 5, 6 when you actually do the printf, and it'll be like OX4141, and so you know it's address 6. Again, if you've never done a printf, I highly recommend, there's other YouTube videos that'll go into a lot of depth and will be way better explaining it than I ever will be. But like I said, this is just how you do it in practice. So then we do the writes, and it'll overwrite the global offset table with this. And we might actually be able to see, actually, I'll do it at the end. Next, then we write it out. We'll receive until we see the word lyrics. Oh, we can actually see what this program looks like when we run it. Lyrics, never going to give you up. I think it already says that. Never going to give you up, never going to let you down. Never end. Oh, I think this is the line it inserts right here. So it just prints a bunch of stuff. And like I said, the next bug we're going to be exploiting is an info leak. So if we were to put a bunch of %p's in here, you can see we start leaking values off of the stack. So this is a stack address, nil, nil, nil. This is some random value. We specifically want a libc leak. So when I get these sort of challenges, I write some code that looks like this. So I just need to leak a whole bunch of values until we see a value that looks like a libc address. Usually when it starts with a 7ff like this, you know it's a stack address. We want a value, let's break in main again. Continue, oops, run. So these are all the different memory segments. So like I said, if it starts with a 7ff, it's probably a stack address. We want a libc leak, so we want a OX7F9. And so we can actually just do this. Print p dot send line out p dot interactive Python 3. Hopefully this works. Cool. So we got a couple of different values. I guess it doesn't print too much out. So like I said, I do 40. Oh, I commented something else. This. There we go. There we go, much better. So I sent this line, so 40 is equal to %40 $P, 41 is equal to $41 $P, and so this is saying take the 40th element on the stack and do a %P on it, and so our response is this. So we can see the 40th element is this, the 41st is this, the 42nd. I started from 0 to 20 and then I did 20 to 40, and then element 40 was the first one that looked like a libc address, and we can see that 7f. And if we were to load GDB, we'd see that this is a actual value within libc. And so we now know that the 40th element, so if I was to do another %40 $P, that is our libc leak. So we'll construct that. So let's comment this back out, comment these two back out. We now know where the libc leak is. So instead of printing out all of those, I only print out the %40. That's our libc leak. Then I'm going to parse it, grab the leak. I get this question all the time, how you calculate these values. So let's actually, we'll do a GDB, or sorry, appone.gdb.attach p, and let's break on actually that return address. Which one did we decide on? This one. And so we're gonna insert this. So this will, Pwn tools will attach GDB to the process, and we're saying break on the address, our return address. So at the start of every loop, it'll break here. So then we can do a Python 3 solve. What am I doing wrong? Oh, tmux. Python 3. Oh, am I working remote? Oops, sorry. I was running all of those remotely against the challenge server. All right, I'm gonna make this a little bit smaller. A little bit bigger. Okay. A little bit bigger. Cool. All right, so let's see where we are. So we leaked a libc here. So like I said, we do that %40, and its response was libc and then the value of %40. So this is our leak to libc. We don't know what it is. We just know it's some address within libc. We also know if we load vmmap that libc actually starts right here. So this address is going to be randomized every time. I think maybe these bytes are randomized every single time. 1, 2, 3, 4, 5, 6, 7. So 7 nibbles are randomized. Again, we don't know where it's going to be, but we always know that the difference between this value and this value will always be constant. And so what I do is, for just whenever I figure out which value I want to leak, I copy one of these. So we can take that one and I put it here, and I copy this one and I put it here. So like I said, this value, no matter if we were to run it again, we can run it again real quick. We'll do continue. I probably should have done the math, but we'll see. I can then, if I was to calculate the difference between this one and the VM map, it'll be the same as the difference between these two, because we're just taking our leak and we want to know how far away it is from the base of libc. And so that's how these values are calculated. I just copy them over from one of the executions, and I know it'll be the same difference for all the executions. Sweet. And then, so now that we have a libc leak, the last step, easy step, we're just going to use one gadget. If you haven't heard of one gadget, it's an amazing tool. Gadget, and we run this on libc. Basically, when you call one gadget, what it's going to do is it's going to calculate all addresses such that if you just jump there, it'll call this line. So if you jump to this address plus the base of libc, it'll execute execve bin shell. And so, or this one, or this one. I mean, it's just absolute magic. There are some constraints that need to be met. So for this one, either the address that R12 points to needs to be null, or R12 needs to be null, or the address R13 points to needs to be null, or R13 needs to be null. And there's similar constraints for this one. I think for this challenge, I found out that these constraints work the best. So absolute magic. So if we can get a jump to this address, it'll execute bin shell, and then we have shell on the box. So to do that, I think I used printf, yeah, so we don't need this anymore. I think I found out that I just stepped through the program. I found out that RSI and RDX, the constraints here, were the easiest to match, and those will be at a good address right before printf is called. So this was just, again, it's just guess and check work. Within GDB, I used the got command to see which values I can overwrite, and I think I just jumped to printf and I saw that RDX and RSI were a good value, so we're going to overwrite the global offset table for printf with our one gadget address. Cool, so load this in. Again, very easy to find these. You just go GDB, rickroll, break, main, run, global offset table. So here's our global offset table entries. So I grabbed the one for printf, so that's 4028, 4028. Then the one gadget addresses, so I usually just paste it down here. So these are the different entries. Sometimes I'm lazy and I just try all three of them and see which one works. This time it was the last one that worked. So we just take this value, we add in the base of the libc, and then again, we're just going to do another format string. Again, to figure out where this offset is, you just send a payload that looks like this. This case that happened to be the 8th one was AAA, so 1, 2, 3, 4, 5, 6, 7, 8. So when you print this out, it'll just do, actually we can show what that looks like. We'll send this line. So we'll do a Python solve. Continue. Yeah, here we go. So it sent this line, and we're trying to figure out which offset references this. And so we can see here's the AAA. This is not AAA, not AA, not AA, not, and there's our 41s. So this one points to the AAAs. So this is the 1, 2, 3, 4, 5, 6, 7, the 8th element. And so that's how I calculate this 8 right here. And so we know it's now this address, the first address will be the 8th offset. We again construct that writes buffer. So again, the printf global offset table is going to be equal to our one gadget. Pwn tools and all of its glorious magic will construct our final payload. And if you want to see what these payloads look like, we probably have it sent somewhere. Yeah, this is what the payload looks like. This was our initial one for overriding that global offset table so that the program repeats. I'm very thankful we don't have to construct these ourselves because it is a pain. Then it will send the line and we should have shell. So did I revert everything? I think so. Probably shouldn't be using GDB anymore. Command aborted, can't insert address. Oh, I think it executed, but it tried to insert our breakpoint into the new process. Oh, well, anyways, I mean, you can see we have shell here anyways. So we have shell running locally, I'm running as loop. And so we could grab the flag, and if we want to test it on remote, we'll comment this out, open up that, Python solve. Let's see if it's still running, and that's local. Did it not save in time? There we go. I think I was a little bit too fast with it. We can count out the flag and it says printf gave me up and let me down. So overall fun challenge. Like I said, there's 3 different steps. We're changing single shot to multi-shot execution. We're going to leak libc, and then we used a 1 gadget to get a shell. So fun challenge. Thanks again, Applet. If anyone has any questions, feel free to message me on Discord or leave them on the comments, and we'll see you in the next video. Cheers.